speaker of the day, that is Kimitoshi Yamazaki. So it is my pleasure to introduce our first speaker, that is Kimitoshi. He received the PhD degree from the University of Tsukuba in 2007. And from 2007 to 2012, he was a project assistant professor in the University of Tokyo. Then he joined Shinshu University in 2012, where he is currently a professor. And his research interests are in robotic vision and version planning. Then he joined. So thanks a lot for being here, and the floor is yours.
Thank you. Wait a minute. Okay, thank you, Onaidas, and good morning, everyone. My name is Kimitoshi Yamazaki. It is a great honor for me to have this opportunity to talk. The title of my talk today is Cross Manipulation Based on Hierarchical Shape Prediction. Before starting to talk about today's topic, I would like to introduce my first study of cross manipulation. The video above left shows the work that led to this. Here, a dual-armed mobile manipulator performs various chores. One of these actions is to find a piece of fabric in a room and pick up it. However, since cross does not have a specific shape, one challenge was how to find fabric products in the everyday environment. We proposed an image processing method that responds to wrinkles. Using this technique, the robot can locate fabric products as shown in the video below left. The process flow is shown on the right. There is a learning phase in which SVM builds a discriminator that responds to wrinkle-like image regions. After that, an input image is divided into three categories: wrinkle-like areas, areas that may not be wrinkles, and an area that is neither part. Then, graph cut is applied, and we obtain a region of the fabric products. In hindsight, this was a very simple method. Okay. After the work I've just introduced, I began to try to achieve more complex manipulations than just detecting and grasping. On the other hand, I also realized that there are many difficulties in manipulating a cross with a robot. What I talk should go without saying for everyone here, right? A cross is a deformable object. This deformability is a factor such as infinite shape state, complex shape, and complex contact and friction force with surrounding environment. Therefore, modeling, recognition, and manipulation of cross become difficult. However, humans have a high capacity for deformable object manipulation. Therefore, it should not be impossible to achieve this with a robot. For such reason, such kind of research team is very rewarding, I think. Okay, from here, I start the main topic of this talk. Introduced at top right is my colleague, Professor Sophie Arnold, who plays a central role in this work. First, we conceptualize cross-folding task as shown in the figure, this figure. Before starting manipulation, the goal state is given. Then, sensor data for initial state are obtained. To realize the goal state, robots must predict cross shape and plan the manipulation procedure, include any midway states. We refer to this level as plan level. Okay. The robot then manipulates the planned steps one by one. Here, the motion trajectory should be controlled by predicting how the cross shape will change during the manipulation. We refer to this level as the manipulation scale. Now, I said two kinds of shape prediction are needed. The title of today's talk comes from this fact. To realize cross manipulation as conceptualized on the previous slide, we are building a dual level system as shown here. In the plan scale, overall motion planning, including midway state generation, is performed. In the manipulation scale, which is for executing each step, the cross shape is predicted and controlled by appropriate perception and manipulation, which are online process. Let me now explain in a little more detail. The first part is to estimate the shape of the cross from the sensor data. A mesh structure is used to represent the shape of the cross. The nodes of a mesh are usually represented by deterministic values. We basically use that representation. However, there will be some areas where the results of shape estimation are not reliable. In the case of deformable object, one challenge is that the shape in occlusion area is unknown. Therefore, a probabilistic representation consisting of a mean and a variance is also introduced in intermediate process of shape estimation. The below right is an example of adding uncertainty to the shape. The goal of shape estimation is to reconstruct the cross shape from a 3D point cloud. Our approach is to generate a cross mesh that is consistent with both the observation and the non-cross topology. We chose to solve this problem as an optimization problem as shown in the blue box here. The procedure begins by estimating the initial values of the mesh from a point cloud. This is here. Then we optimize the geometry and the topological constraints of this. I will explain this procedure step by step. First, we obtain 3D point cloud data, SPC, from the sensor. Then, we convert the point cloud into a voxel representation. At this time, we boost Z coordinates to capture more fine height detail, such as cross wrinkles. Then, we estimate the cross shape probabilistically using the voxel to mesh network. We call this the V2M for short. The input of the V2M is the voxel representation, and its output is a probabilistic cross mesh. The probabilistic mesh format describes vertex positions as 3D multivariate normal distributions. Finally, we derive a deterministic estimate using a topological refinement procedure. By minimizing the vertex positions negative, we ensure consistency with the observed shape. By minimizing a topological loss, we improve the realism of the estimated shape. Next, I will give a specific explanation of the plan scale here. The method we proposed is EMDNet. This is a modularized neural network, encode, manipulate, decode network. This neural network consists of 3 parts. The encoder here compresses the shape data, and the manipulation network predicts the deformation caused by the manipulation. And the decoder then reconstructs the shape after manipulation. There are 2 inputs, current shape S sub I and the manipulation input M sub I. Output is the predicted shape S sub I plus 1 after virtual manipulation is added. Okay. EMDNet has 2 functions, shape prediction and manipulation planning. Shape prediction is performed by propagating the network in the forward direction. The predicted shape after manipulation is obtained as a mesh representation, like this. Next, we discuss manipulation planning. Manipulation planning is performed by propagating the error here between the predicted shape and the goal shape S star backward through the network using the error back propagation method. The inputs to the manipulation plan are the current shape and the goal shape. The outputs are the manipulations and the shapes between manipulations to deform to the goal shape. This planning makes it possible to deform to various goal shapes. Furthermore, as shown in the figure on the right, 2 or more manipulations can be performed by connecting multiple network. This is an important point of the our proposed EMD-net. Here is an example of the planning. Current shape is unfolded rectangular shape. The goal shape is shown here. From these inputs, EMD-net outputs both manipulation and intermediate cross shapes, as shown here. Okay, the manipulation consists of peak and release points, as shown in green and red dashed lines. In this case, 3 manipulation steps were automatically generated to obtain a shape that is similar to the given goal shape. Next, I will give a specific explanation of the manipulation scale, shown in the bottom. For the manipulation scale, we assume that the initial state, a final state, and the initial trajectory are provided by the Planck scale. And we aim to solve the manipulation scale using 3 core functionalities. That is, shape estimation, which I have already explained, and shape prediction, and the trajectory correction. The accuracy, flexibility, and the execution time of these 3 functions must all be at practically applicable levels. Core features of our approach are that we use a mesh format for cross-shape representation and learn a forward model of the object dynamics for real-time shape prediction. Here, we explain about online manipulation trajectory correction. The goal of trajectory correction is to make the manipulation outcome S sub n here match the goal shape S star, this one. Formally, we minimize the objective function shown here. To achieve this, we predict the outcome based on step-by-step shape prediction and adjust the manipulation trajectory so that the prediction matches the goal. First, we initialize the manipulation trajectory and estimate the current cross shape. Then we start the manipulation. Manipulation follows the following procedure. First, we predict the final manipulation outcomes S hat sub n here and calculate its error relative to the goal shape S star. If the error is above a set threshold, we trigger trajectory correction, revising the trajectory to reduce the error using back propagation through the prediction network. Alternatively, the error is below the threshold, the robot executes the first one-step manipulation and obtain a new estimate of the resulting shape. By repeating this procedure until all waypoints of the trajectory are processed, we get a trajectory so that the target object into the goal shape. These procedures can also be performed during manipulation. In other words, it is possible to correct the trajectory while folding. Okay. Next, I will introduce our experiments. To verify the feasibility of the proposed method, we set up a task to fold a square piece of fabric. Since it is difficult to collect training data only in the real world, we use a physics simulator to collect various folding data. And Kawada Robotics Hero, a dual-armed robot, was used as the actual robot. And the RGBD sensor was placed in a position directly opposite to the robot. The picture on the right shows the experiment in progress. The training data necessary for training the networks used in the experiments were collected using the following setup. First, we decided manipulation method, that is, operate with one or both hands, and grasping position is limited to the corners of the fabric. The hand is assumed to move in a circular arc, and ArcSim was used as the simulator. As shown in the movie on the right, ArcSim provides accurate and stable cloth behavior. In one simulation, the cloth was folded 3 times. The shape of the cloth at rest and the shape of the cloth during manipulation were saved. The number of data collected was over 3,700 sets. Okay. This slide shows a trajectory correction example. The evaluation conditions are as follows. We initialize the trajectory as an arc-shaped curve. The grasp points are defined by the initial trajectory. We evaluate 3 test scenarios. In scenario 1, manipulation proceeds undisturbed, like this. In scenario 2, friction is lowered, causing the cloth to slip during the manipulation, like this. In scenario 3, an external disruption is applied partway into the manipulation, here. Okay, the figure and the animation in the middle right show an example of manipulation with correction in scenario 3. We observed that with correction, the trajectory was modified appropriately, this blue line, in response to the external disruption. Okay. With correction enabled, the error is about 5% of the cross size. This table shows the results. We also performed experiments using actual dual-arm robot. This diagram shows the example. This diagram shows a unified system combining plant scale, as shown in the pink square, and manipulation scale, as shown in the blue squares. So the plant scale provides intermittent cross shapes, while the manipulation scale generates and modifies trajectories in detail. Here are 2 videos about one folding action. The left side shows the results when a disturbance is applied during folding. The robot realized midway through that the desired shape was different from the current shape and corrected its trajectory on the fly. By the way, the robot's motion is not smooth in this movie. This is because a new trajectory cannot be generated until the shape prediction result is known. So a wait time is required immediately after the estimation. Since this does not look good, we built a control loop that takes the delay into account. As shown in the right movie, the result is the smoother and quicker motion. Using the system mentioned in the previous slide, the robot solved a folding problem, this initial shape and the target shape. The left bottom movie shows the first manipulation, and then the right bottom shows the second manipulation. In both steps, one hand manipulation is automatically selected and generated. A similar shape to the goal state was obtained. I think we still have a little time, so I will introduce some of our other research results. We also apply reinforcement learning and imitation learning to cross manipulation tasks. The upper left movie shows how to lift a folded cloth without losing its shape by reinforcement learning. In the movie below, the robot learned how to fold a shirt while placing it on its chest. On the right is our proposed policy model. It processes two things simultaneously, that is, segmentation of a task into multiple simple actions and reinforcement learning of each action. The bottom right videos show that the proposed method falls better than the single policy for.
Amazingly.
People know how to use Zoom now.
Okay. If we want to manipulate the cloth quickly, we need to understand dynamic shape changes. We have been working on this issue. In the movie above left, we focused not only on the deformability of the cloth, but also on its stretchability. The wrinkle pattern created by the pull is used to pass a hanger through a narrow neck hole. Okay. The upper right and lower left videos show assistance in dressing. Here, optical flow is used to cloth shape estimation. This enables faster detection of snagging than force sensors. In addition, this approach allows the robot to continue moving without stopping during recognition process. And the lower right shows the assistance of dressing according to human movements. The hybrid control of position and force prevents people from being burdened. We are also working on an efficient and stable method of cross manipulation. The video above left shows what we call pinch and slide unfolding. The hand is moved along the edge of the fabric for efficient unfolding. The right video shows an end effector for more stable manipulation. It performs also the pinch and slide unfolding, and it can stably manipulate the cloth. As shown in the bottom movies, we are also developing end effectors in collaboration with a manufacturer of industrial sewing machines. It can pick up a single piece of cotton fabric that is thin and easily adhered to each other. As shown in the center movie, the end effector is highly repeatable. The same end effector can also be used to pick up woven rubber, as shown in the bottom right movies. Okay, today I presented cross manipulation based on hierarchical shape prediction. We have organized the problem of transitioning the cloth to the desired shape. Two planning scales, plan scale and manipulation scale, are introduced. Then we presented feasible solutions for each scale and how to integrate them. My interest in deformable object manipulation is boundless. Therefore, we will work on quicker cross handling. To achieve this, we work on estimating the dynamic state of the cross and controlling its shape. Efficient learning of cross manipulation is also important. Since a cross can have an infinite number of states, it must be able to appropriately construct a feature space that represents the relationship between manipulation and shape changes of the cross. In addition to these standard directions, I'm also interested in the elucidation of the mechanism by which people understand deformable object manipulation. Okay, before I finish, a few words. My colleague, Professor Sobi Arnold, is now planning a special issue at Frontiers in Neurorobotics. I kindly introduce you. Please consider contributing. That's all. Thank you very much for your attendance. If you are interested in our research activities, let's collaborate internationally. Please do not hesitate to contact us. That's all. Thank you very much.
Thanks a lot, Kimitoshi. So now it's questions time. So I just want to remind the audience, you can just raise your hand or write in the chat on the Zoom and also use the Slido. So we already have one question. It's from Ariel in the Slido. And he's asking, how is the manipulation represented in order to be fed into the network?
In Slido?
Yeah, you can find the link on the website.
Yes.
Maybe I can also send it here.
Mm-hmm. Oh, it's a very difficult question. Manipulation. How is the manipulation representing the fed into the network? Because we have two types of prediction network. So this is one of them. Sorry, I cannot understand very well about this question. So can you explain about this question in more detail? Someone?
Well, Ariel, maybe if you're joining the Zoom or you're in the room, you could probably just
Martina?
explain. Yeah.
I think there's a few people in person who have question too.
Yeah. Yeah. Okay. So we can go.
Have any questions here? I saw a few hands. You might have to walk to the microphone if that's okay. All right. So we have one question now.
Yeah. So that's me who asked the question on the.
Oh, okay. Great.
So
Perhaps I can answer this question. So
I'll try to explain. So I guess you
Okay.
explain how the
can I answer it?
the mesh.
So the manipulation is very simple. Picking up
Just a
point.
moment, Kimitoshi. So they
Okay.
are repeating the question in the room.
Mhm. Okay.
Okay, I think you actually need to come here. So the
No,
he here sits. No, he needs to speak in this microphone so the Zoom participant can hear it.
Yeah. So otherwise, you can just repeat it. Hello.
No, it's a computer. It's this computer.
Okay. Well, I'm the first to ask questions, so I guess I'm hitting all the glitches. Sorry about that. So I was asking, I understood that the object is represented by a mesh. I'm wondering, how is the manipulation represented? I guess it needs to be represented somehow in order to be fed into the deep network.
Mhm.
So what
Okay.
this representation is?
So the manipulation is simply represented by the point and the lines. I have no slide about it, but so there is two candidates of the picking points, and after the points picked, the trajectory is just linear trajectory. So the robot detect pick and points. It is represented by the 2D coordinates, and after that, the distance to move the other part to folding. So maybe we have 6 degrees of freedom as manipulation input. Is it become the answer for you?
Yeah, thank you very much.
Yeah, thank you.
Okay, thank you. Are there any other questions?
Yes.
Yeah, I think there's one more question in person.
Yeah, okay. Let's go through the one in person. We have another one on Slido then.
How frequent does the trajectory operation have to be run to ensure accurate manipulation? Okay, so.
Okay, let me read the question so that everyone can know it. So now we are addressing the question from Thomas on Slido. That's how frequent or infrequent does the trajectory correction have to be run to ensure accurate manipulation?
It is a parameter to investigate for us. And we decided to about 6 millimeters per one manipulation, because we have about 200 or 300 millimeters for one manipulation trajectory, and we divided the trajectory into 50s. So it means about 6 millimeters. This was our findings as good good frequency.
Okay, perfect. Thanks. So, Daniel, you said there is another question, right?
Yeah, we have one more question. I think you also just come to the laptop. We have to figure it out how to do it more efficiently, but I think
we are sorry.
Hi, I may have missed this, but I was wondering, when you're estimating the state of the mesh, how do you handle occlusion, and do you make any assumptions on the shape of the cloth? Do you have any thoughts on how to generalizing these to different types of fabrics? Thank you.
Okay. In the present, we tried just a simple shape, so maybe it is not the general knowledge, but in our case, we estimate the mesh from the point cloud, but here we may have occlusion. In such a case, such occluded part is estimated with the probabilistically. So after that, we optimize the shape by using the topological constraints. So it means the neighboring points existing near of the present points. Using these topological constraints, after we get this deterministic shape, so using this procedure, we cope with the occlusion part as the some hypothesis and so deterministic shape. Sorry, just a difficult point to answer this question.
Okay, great. Thanks a lot. I don't know if there are any other questions.
I think we have one more quick question. Yeah. Although I think this is the last question, and then we have to move on to the next speaker.
Yeah.
It sort of builds off the other one. Oh, so what sorts of cloth configurations do you expect the system to break down? Like, are there certain shapes you've just tried informally where you just think it just wouldn't work very well and more sensing might be necessary?
Oh, sorry, I don't hear you very well. So
speaking,
please.
Okay. What sorts of cloth configurations do you expect the perception system to break down? Have you tried any informally where you think that more sensing might be necessary?
Sorry. Sorry, I cannot answer now. So please contact me after.
Okay.
Okay. Sorry.
Okay, then